For decades, we've pretty much been told the same story. The future of energy is all about building a better battery. But what if the answer isn't about chemistry at all? What if it's about harnessing one of the oldest forces we know, just pure raw momentum? Okay, you're going to want to stick around for this, because today we're diving into why some of the smartest people in energy are burying massive spinning wheels under our cities to power the grid. So let's just start with that one big question, right? A question that kind of pushes back on everything we think we know about storing power. I mean, we all have lithium-ion batteries. They're in our phones, they're in our cars. They are the undisputed champions of the energy world, no doubt. But what if that champion has a fatal flaw? Or maybe a few of them? And this is where we get to the dirty secret of our chemical batteries. Over on the left, you've got the champ, but it degrades with every single charge. It has a very real fire risk from something called thermal runaway. That's where it can just start uncontrollably overheating. And, of course, it relies on mining rare and often controversial minerals. But look at the challenger on the right, a technology that has basically zero degradation, a failure mode that's mechanical and safe, and it's built from common stuff like steel. So what is this challenger? Well, here's the crazy part. It's not new at all. In fact, it's an idea that goes back thousands of years, all the way to the simple potter's wheel. Yeah, we're talking about the flywheel, an ancient concept that has been completely reimagined for the modern age. You know, the concept itself is just beautifully simple. Instead of storing potential energy in all these complex chemical bonds, a flywheel just stores kinetic energy. It's the energy of a massive spinning object. Think of it less like a chemical reaction and more like a perfectly wound spring, just waiting to unleash all that power. It's truly a mechanical battery. So how in the world do you take an idea from a potter's wheel and turn it into something that can stabilize a city's power grid? Well, it takes some seriously impressive engineering. So let's peel back the layers, let's look under the hood and see the anatomy of one of these modern flywheels. Okay, first things first, you have to get rid of air. Seems simple, but air resistance, or drag, would just suck the energy out of a spinning wheel in minutes. So the entire rotating part is sealed up inside a chamber where they've pumped out nearly all of the air. This creates a near-perfect vacuum, and that's really step one to achieving this incredible efficiency. Next up, you've got to eliminate friction. We're talking about speeds over 50,000 RPM. Traditional ball bearings, they would literally just disintegrate. So, what's the solution? Magnetic levitation. The spinning rotor actually floats on a magnetic field. There is zero physical contact. It's a completely frictionless spin. I mean, that is just incredible. So, how do we get power in and out of this thing? Well, a single really clever device does both jobs. See, when you have extra power on the grid, it acts as a motor, using that electricity to spin the wheel faster and faster. It's basically charging it with momentum. But then, when the grid needs that power back, the device flips its role. It becomes a generator, drawing on the wheel's momentum to create fresh electricity. Now, this is where it gets really, really cool. The secret to making flywheels powerful enough for the modern grid isn't just about making them heavy. It's all about making them fast. And the physics behind why this works is both super simple and honestly pretty profound. The whole magic trick is right here in this formula. The energy a flywheel can store is proportional to its mass times the square of its rotational speed. See that little omega squared? That's the one. It means that speed is exponentially more important than weight. That little squared symbol is the secret sauce, and it has a massive impact. Let's look at what that actually means in the real world. So here's how that math actually plays out. If you double the weight of the spinning rotor, you get to store double the energy. That's good, right? 2 times is great. But if you double the speed of that rotor, you don't just double the energy. You quadruple it. 4 times the energy for 2 times the speed. And that is why engineers are completely obsessed with making these things spin as fast as humanly possible. Okay, so now we get how they work, but the big question is, why should we care? What actually makes this big spinning wheel a real contender against the absolute dominance of lithium-ion? Well, it really boils down to 4 key advantages. You could almost call them superpowers. First off, unlike a battery, a flywheel just doesn't degrade. You can charge and discharge it hundreds of thousands of times over a 25-year lifespan, and it's just as good as day one. Second, it is unbelievably fast. We're talking huge bursts of power delivered in milliseconds.
Third, it's green. It's made from common recyclable stuff like steel, not rare minerals with toxic chemistry. And finally, because it's spinning in a vacuum, it couldn't care less if it's in the middle of the Sahara Desert or the frozen Arctic.
So these advantages make the flywheel uniquely suited to solve one of the biggest headaches of our modern energy grid. And it's a grid that's getting more and more, well, nervous and unpredictable, especially as we add more renewables like wind and solar. This whole problem is perfectly captured by a phenomenon with a funny name, the duck curve. Basically, the grid gets totally swamped with cheap, clean solar power during the day. But then, poof, the sun goes down right as everyone gets home from work and starts turning on their lights and TVs. This creates these huge, rapid swings that the grid really struggles to handle. And this is where the flywheel just shines. It acts like a mechanical shock absorber for the entire grid. It can sense the tiniest fluctuations in the grid's frequency and instantly, I mean in milliseconds, either inject power or absorb excess power, keeping the whole system perfectly balanced. They are absolute masters of stabilization. So, yeah, the future looks incredibly promising for this old but new technology. But, just like any good hero in a story, the flywheel isn't invincible. And it's really important to understand its limitations, too. The vision for the future, though, is amazing. I mean, people are talking about huge underground farms of these flywheels stabilizing entire regions. Or imagine individual units buried deep beneath skyscrapers to provide uninterruptible power. NASA is even looking at them for use in space, where they can do two jobs at once, store energy and help aim satellites. But here are the challenges. The number one limit is just plain old physics. Spin something that fast, and the centrifugal force can literally cause the rotor to shatter. This means they need heavy, expensive containment vessels for safety. And also, they do lose their charge, their energy, faster than a battery over time. This makes them perfect for those quick, short-duration adjustments, but not for, say, storing summer sunshine to use in the dead of winter. So what's the big takeaway here? It's that the future of energy isn't just one single solution. It's going to be a whole team of them. And as we move away from the old power plants that had a lot of physical spinning mass, we're rediscovering that the simple, elegant physics of a spinning wheel might be exactly what we need to build a faster, cleaner, and way more resilient grid. The future, as it turns out, might not just be electric, it's kinetic.